All right, let's try another application of partial derivatives. Okay, example 7. The reaction to X units of a drug T hours after it is administered is given by this multivariable function, R of X comma T equals, and that looks like a bit of a mess with like a, I don't know, a quadruple product rule. But it won't be quite that bad because when we're doing partial derivatives, remember that we hold one of the variables as a constant. Okay, so then this function is just defined where X is between 0 and A, where A is some other constant. Okay, so that's going to be a constant value in both of our partial derivatives. So let's find and interpret the partial derivative of R with respect to X and the partial derivative of R with respect to T. And then of course, the interpret part is the thing that we are really working on getting used to, because that can be the tricky part when there's so many different variables going on. Okay, so let's go ahead and get started with this one, the partial of R with respect to X. So I'm going to write that down as the partial of R with respect to X. So we're going to go through and take the derivative of this thing where we treat T as if it's a constant. So just looking at this thing, I want to see if there's like any cleaning up that we can do to try to simplify our work here so that it doesn't end up a big mess. So we want to avoid giant product rules if we can. And so what I'm noticing here is since the T squared and the E to the negative T, those are both constants right now, right? So what I want to do is, I don't know, it just helps for me if I think about constants as multiplying into the front. So I'm just going to rewrite this as T squared E to the negative T, multiplying in the front. And then I'm going to distribute that X squared in here, and we get AX squared minus X cubed. So I'm just getting this ready, and I want to see if maybe I can just, do a couple of steps here to make the derivative easier. Because now what I also want to talk about is, if you recall, we've got some nice derivative properties from the past. So if you recall, if you have f of x, or if you have y equals f of x compared to y equals a constant times f of x. Okay, and so this is the one that we're dealing with right now. If you recall, dy dx, so just the derivative, it's just going to be the constant times the derivative. We're actually able to bring that constant out in front and just pretty much ignore it as long as it's a constant multiple. And so it's got to be a constant multiple. Another way we can think about that is if we do like the derivative of k times f of x, then that's the same as bringing the k out front and then doing the derivative of f of x, like so. So kind of some scratch work there to just get some ideas for how we can handle a constant multiple times the stuff that we're actually holding as the variable. So with all of that being said, all I want to do is I want to realize that that t squared e to the negative t, that's just a constant multiple. And then now I can go through and find the derivative with respect to x of all of the stuff in there. Okay, so then a, again, that's just some constant. And so the derivative by the power rule is going to be 2 times that a, x to the first power, reduce the power by 1. And then in the second part, power rule 3x squared. So a little bit of fancy maneuvering there to get the function to look a little bit nicer, but that's pretty much how I'm going to leave the answer there. Maybe I could factor out the x on the inside, but nah, I think it's pretty good just sitting like that. So I'll leave that as the answer for the partial derivative. So now we need to interpret what this means. So it's really important to realize what is this function representing. So this is the partial derivative of the function r with respect to x. So it's going to be the change, right? The rate of change of the r function, which is the reaction. Okay, so this gives the rate of change of the reaction function. Okay, so that's what the derivative is going to do. This gives the rate of change of the reaction. And we're focusing on the variable x. So x units of a drug. Okay, so this gives the rate of change of the reaction, which R is the overall function. And then now it's with respect to which one of the variables. Okay, so it's the rate of change of the reaction per unit change. Okay, per 1 unit change. And they didn't tell us what the units were. It could have been like milliliters or cubic centimeters or whatever it is. But we know that it's per 1 unit change in the amount of drug. Okay, and we can just go ahead and end it there. We don't need to talk about T at all because we were holding T as a constant, doesn't even matter. Okay, so that will be our interpretation of the partial of R with respect to X. So now let's work on the partial of R with respect to time, okay? And so just thinking ahead about this should give the rate of change of the reaction per unit change in the time in hours. Okay, so they did say in hours, so we could probably be a little bit more specific. And instead of saying per unit change in time, we could probably say per 1 hour after it's administered. So I'm getting ahead of myself there, but I just want to get the mind thinking about what this actually is going to represent. So let's work this one out. So I'll erase my little distributing marks here because I want to see if maybe we can clean this up a little bit before we start. Because this time, T is the variable and X is the constant. And so looking back at this here, I'm not going to do my, my other version there. I'm going to think about T squared and multiplying by e to the negative T. It looks kind of unavoidable that we're going to need a product rule here. Okay, but I'm going to do that same process where all of this, that's just all a constant now, right? So the x squared times a minus x, that is all just a constant. And so we can go ahead and just do that same property where I'm going to leave the constant multiple out in front. And it's going to multiply by the derivative of the actual function in question, which is a function in t this time. Okay, and yeah, that one, unavoidable product rule here. Okay, so let's go ahead and do the product rule with the t squared times e to the negative t. Okay, so product rule says first times the derivative of the second. So the derivative of e to the stuff is itself times the derivative of the stuff. So don't forget that chain rule. The derivative of negative t is -1. Okay, so that's first times derivative of the second plus the second. I just like using a bunch of extra parentheses to emphasize which piece is going where. Okay, plus the second times the derivative of the first. Okay, so power rule there. Okay. Now let's clean this up a little bit. And so let's see, this x squared, a minus x, just looking back at the original function, that's just there again. So I think it's okay to just go ahead and leave it as a multiple outside. It's better to put it in some kind of a factored form rather than distributing everything out. And then looking on the inside here, well, I'm noticing that if we started trying to clean this up a little bit, there is an e to the negative t in both locations. And the original function had the e to the negative t factored out on the right-hand side. So, oh, why not? Let's factor out that e to the negative t on the right-hand side. Okay, so then what's left in here? We would have this -1 times t squared, and we would have plus this 2 times t. So we could even like factor out another t if we wanted to. But I'll just go ahead and leave it. I think it's a little bit cleaner factoring out that e thing and then leaving all of the regular t stuff inside. So I kind of like the idea of doing the positive first for the 2t. Okay, so I'm doing this one first. And then because of this -1 that will go with the t squared, then we can go minus t squared. Okay, so I'll go ahead and say that that's good enough for the partial derivative with respect to t. Okay, and yeah, you could factor one of those t's out as well, but I'll leave it at that. So let's actually write down what this means then in the context of the problem. Okay, the partial of r with respect to t. Okay, so that's going to give the rate of change of reaction. So let's write this down. This gives the rate of change of whatever the function is defined as. Okay, so that r right there, it's the rate of change of, and this function represents the reaction. So it's the rate of change of the reaction. Okay, and then this time we're talking about the variable t. Okay, so instead of talking about like a per unit change in time, we can get a little bit more specific because they were talking about t represents hours after it is administered. And the reaction or these rates of change with these partial derivatives, we always want to think about it in terms of per unit change. Okay, so if we want to go per unit change, that would be 1. Okay, think about units just means 1. So if the units are hours, it would be the rate of change of reaction for a 1 hour change in time. Okay, so that's the per unit change, and we can get more specific per 1 hour change. Okay, in time. And it's just what did it say? Time after it's administered. Okay, so time after the drug okay. So very important to read the problem carefully, realize what is the function itself representing. And so that's the rate of change of the overall function. And then it's with respect to one of the variables, and that's going to be a unit change in that variable. Okay. Takes some getting used to, but hopefully it's gradually starting to make a little bit more sense about what you need to look for to write down the interpretation of what everything is representing. Okay, I'll go ahead and put a box around that first partial derivative too. Okay, we never needed to really focus on a being a constant, just being careful that we understood that that was a constant in the problem, and then this little domain here for x, we didn't really need to even talk about that either. Okay, so that's example 7. I believe I have one last example. Yes, I will make one last video to finish off with example 8. So stick around for that.